Okay, so you wanted to talk about how to solve number three on the week three assignment. Okay, so that's what we have set up here. Okay, so you notice we have our two boxes on the slope. We have the positive X and Y direction set. So then what we're going to do is we're going to start putting in the forces that let us know what's going on. Okay, so these are going to be tensions. Okay. All right, so let's think about what other forces we have present. So both of these are going to have a gravitational force. Okay. So let's see, what's this? Mass one times gravity, mass two times gravity. They are going to have normal forces that are going to go out perpendicular to the surface. And then they're going to have components for each of the gravitational forces. Nope, did that backwards. That is the y component, x. Okay, so this is everything that we need. We can note that theta, 25 degrees, the gravitational constant, 9.8 meters per second squared. Okay, and then let's also make note of the fact that inside of each one of these little triangles, that is also the angle theta. So for tension one, we can just use the first mass. Because again, we don't have to really take into account the whole system because that tension is going to be the same for both masses. It's just pulling in opposite directions. Okay, so we're going to do our net force in the x direction. There's going to be T1. Then remember that mass one, each mass is still going to have its. So if I moved it up here, that is going to be the x component of the gravitational force. So that's going to give us. And it's not moving, it's an equilibrium system, so it's equal to zero. If we look at the positive directions, we see that tension one is positive. The x component of the gravitational force is negative. So we can solve for the x component of the gravitational force, and we know that this is going to be m1g. And then we look and we see it's going to be uh, sine of theta. Then we put in our numbers. And at the end, this is going to give us our tension 1 is 8.3 newtons. So that solves for that first tension. Now for tension 2, we're going to have to use mass 2. And again, we're going to do our net component in the x direction because, I mean, if you look, the y components, the normal force, and the y component of the gravity, they're just not going to come into play here. So let's solve for tension 2. So we're summing together our x components. Okay, so what do we have? We have tension 1, we have tension 2, and then we have the x component of the gravitational force, and that equals 0. So let's go back and look which way these are pointed. Now for mass 2, tension 1 pointed in the negative direction, tension 2 pointed in the positive direction, and then the x component of gravity is pointed in the negative direction. Okay, so that's going to give us T2 is positive minus T1 minus M2 G of x, G sub x equals 0. We're going to get tension 2, tension 1 plus the x component of the gravitational force on mass 2, T1 plus M2G sine of theta. And so when we plug in our numbers, because we already solved for tension 1, our 1 kilogram mass, the gravitational constant, and so you see T2 is 12.4 newtons. Okay, so that's all there is to problem number 3. It also looked like you might have been having a little trouble with problem 4. So let's talk about that one. So this is the basic setup. You have these two blocks tied together by a cable sitting on flat ground. So of course, between the two blocks, you're going to have a tension. So, okay, so let's call this block A, block B. So as always, we're going to have our gravitational forces. Now you notice I just called them both mass times gravity. That's because these blocks are both going to be the same mass. Okay, which we'll end up being able to factor out, which is, it makes this nicer. They're both going to have a normal force. There is a force pulling on both of them. That's moving the entire system. And then or that's trying to move the entire system. But then they both are going to have static friction forces. So again, this force is trying to get this system to start moving. Then we're trying to figure out exactly what force has to be reached in order for that to happen. So the way we do that is we talk about our friction force. Remember, the maximum static friction force is the coefficient of static friction times the normal force. And so when we figure out the force we need with this maximum static friction force factored in, anything beyond the force we calculate will get the system to start moving because we will have passed the maximum static friction. So for part A, we're going to look at block A. So you notice on block A, you have, in the X direction, you have tension, and you have the static friction. And let's go ahead and mark X and Y. So those are our positive directions. So you're going to have tension plus the static friction of A. It's not moving yet, so it equals 0. Tension is in the positive direction, static friction is in the negative direction. And so the tension between the two blocks is equal to the static friction of block A. Okay, now we're going to incorporate that maximum static friction. Coefficient of friction of block A times the normal force. We don't know what the normal force is, but we can solve for it. Okay, so to solve for the normal force on block A, we want the sum of the forces, the net force in the y direction. So it's going to be your normal force plus the gravitational force. Due to positive and negative directions, we get N minus mg, or the normal force is going to equal the gravitational force. And so then our static friction, our tension here becomes the coefficient of friction mg. So let's look at this. Let's look at block B for a second. We're going to do the net force in the x direction. So that's going to be the force trying to move the blocks, plus the tension pulling the other direction on block B, plus the static friction force of block B. Okay, so that's going to give me force is in the positive direction, and these other two are in the so the tension and the static friction of block B are in the negative direction, like we said. We can solve the force that we need, so we're getting closer now. Is tension plus the static friction of B. Okay, well, remember tension is the coefficient of static friction of block A, mass times gravity. Plus, and then the static friction of B is the same equation, just with the different coefficient. Okay. And so then we can just factor out mass times gravity. And we have our two coefficients of friction, which we add together. So then the force, that's going to be the 2.0 kilograms, which is the mass of each block, times gravity, which is the 9.8 meters per second squared. So it's the gravitational acceleration constant. And then our coefficients of friction from the problem, 0.45, 0.30, So the force, so the force that you calculate is 14.7 newtons. So then anything beyond 14.7 newtons is going to start this system of two blocks moving, because we used the equation for maximum static friction force for our calculation. So then part B said, what's the tension in the cable between the two? Well, remember tension we solved. It's going to be the static friction coefficient for block A, mass times gravity. And so the tension between the two blocks, 8.82 newtons. So there's problems 3 and 4 from the week 3 assignment. Hope this helps out.